afternoon, everyone. My name is Haitao, and thanks so much for giving me this chance to present part of my research involved in the past 6 or almost 7 years. So today I will talk about 3 topics. So the first one is part of my PhD research project I did from 2012 to 2018 at the Queen's University in Canada. So it's about the horizontal borehole slippability during horizontal directional drilling. And the second topic is we use a facility in our laboratory at the Queen's University. We try to simulate its differential ground motion, and we bury a flexible pipe. And we want to study the structural response of this flexible pipe. And I'll briefly talk about the research I'm doing right now at the Cambridge University. It's still in a very early stage, so there's not much I can talk about. And the last topic is pipe rehabilitation. We use a facility at Queen's again to test a PVC pipe, and the engineer was curious about what's the behavior under the simulating ground pressure during a sliplining. That's one of the methods using in pipe rehabilitation. So first of all, there's a picture on the right. That is the different position at a cross section of the pipe, because I will talk about a lot of this during the presentation, just in case some people are not familiar with. So the 0 or 12 o'clock of the pipe, that is a crown. 6 o'clock, that is the invert. 3 and 9 o'clock, that's a spring line. Between crown and spring line, that is shoulder. And 100 is between the spring line and invert. Horizontal directional drilling, some of you probably heard this before. It's one of the most important pipe installation methods using in Trenchless technology. Imagine you want to install pipeline across a river and lake. You cannot just dig out the trench and put the pipeline in. So the first step is to drill a pilot hole from one side of the river to another according to a drill path. And the second step is to use the reamers to enlarge borehole several times to a target diameter. Usually is 1.2 or 1.5 times of pipe diameter. And the last step is to put a pipeline into the borehole. However, if there's nothing in this borehole will easily collapse. So that's why we pump the mud, that is a bentonite kind of clay, mixes water into the borehole to balance the pressures outside. If this pressure is too high, mud can flow into river and lake, contaminating soil, water, causing ground heave and other problems. So it's very important to investigate what is a failing mechanism in sand and saturated clay, these 2 common soil types, and to figure out what is the maximum allowable mud pressure, PMX, during this process. Yeah, because I don't have the time to talk about all my details, my PhD research. Today, I will focus on some of the tests I carry out in sand. Actually, in sand, we also did a series of tests. We investigated 3 main factors to see how these factors influence on this peak or maximum allowable mud pressure. So we investigated the different pump bury depths, different pump rates, multi-layer systems. That is a dense sand covered by loose sand or dense sandy gravel. We analyzed the data. We did some parametric study, and then we proposed our design equations for industry, because the design equation using industry nowadays is not that safe, which I will talk about later. And then we apply this design equation into some case study to see how it performs. Today, I will focus on the first factor, that is different bury depths, which we have published of this part of the research, I think, 2 years ago now, right? This year is 2021. All the tests we conduct in a pit that is 2 meters wide, 2 meters deep, and 2 meters long. Borehole was located in the center of this pit along this east-west direction. Borehole was located at 0.4 meters above the concrete base, that is around 10 tons of diameter. The side boundary is 1 meter, which means from the center of the borehole to the south or north side of the pit, it's about 25 tons of diameter. Sand was used in all these tests, of course. The strength and stiffness have been qualified using Trenchless test. During backfilling, we measure the densities and water contents in each test and each layer or each lift. And we control the number of lifts or layers so we can get the different buried depths. Sand was compacted into a dense state by using a small evaporation compactor, as shown in this picture. We also bury some earth pressure sensors at the 3 times radius below the invert of the borehole to measure the circumferential, axial, and radial stresses. These sensors also called the Nile gauges, which were developed by Professor Mark Kanisnik from Israel Institute of Technology, because these sensors could give us much more accurate and reliable measurement than the data using the conventional earth pressure cells, because those conventional earth pressure cells will introduce arcing errors. After we finish backfilling, we carefully level the ground and place some target blocks on the north side of the pit. We install 3 cameras on the east, south, west side of the pit. During the test, we take some pictures and input those images into a program called Geoparticle Image Resolumetry, GeoPIF, developed by Dr. Andy Take and Dr. Dave White, I think probably 20 years ago at Cambridge University, and recently by improved by my supervisor at Cambridge University, Dr. Sam Stania. So you can get a better stream results. However, when this method using in this 3-dimensional problem, they will introduce pseudo displacements. So let me give you an example. So it's a very simple example. And here is a picture taken by camera 1. If we move the block, marked as in that red dashed line box there, if we only move that block horizontally, it's no problem for that program to give me the accurate answers. However, if you use the program in another angle, so here's a picture taken by camera 2, that is a 90 degree from the camera 1. For that block, it should not introduce any vertical and horizontal movement because we only move that block horizontally from the angle of the camera 1. However, if we use this program, they will introduce the vertical and horizontal displacement, which should not exist. So that's why I developed some post-processing methods to diminish this pseudo displacement, so you can get the much more accurate results during the test. We also use a structure for emotion and multi-view stereo, as well as a LiDAR, the light detection and ranging, to build those dense point clouds, so we can compare the vertical displacements before and after the tests. In this presentation, I will talk about the results from the GeoPIF. That's the main method I use for this test. After we finish the setup for the ground surface, we drill the borehole using a shabby tube. So this borehole is 1.5 meters long, and then we insert the packer in initial 0.5 meters and inflate it to seal the entrance based on experience during our pre-test. And then we pump the mud into the borehole, and that mud pressure was measured by a small transducer attached in front of the packer. So here is a configuration of this test. So the H is the distance from the ground surface to the spring line of this borehole. Basically, we just change this buried depth to see how this buried depth influence on the mud pressure in this test. During the test, we pump the mud into the borehole, and the volume of the mud in this borehole will become more and more until the mud flow out of the ground surface. So here is one example from our tests. That's HLD of 18 at pump rate 12 liters per minute. So x-axis here, that is the time with unit second, and y-axis is the mud pressure KPA kilopascal. So mud pressure reaches the peak value in a very short time. Before that, that is a pre-peak phase. And after that, it's a post-peak phase. We stop the test when mud appear on the ground surface. So here is a video from this test. On the top, the green line there is the mud pressure history. At the beginning, it's a 0 kPa. And the borehole, if you can see the direction of my mouse, that is the under the first column of the this target blocks. So that's the entrance close to the wooden wall. So let's start our test. You can see the mud pressure build up pretty quick, reach the peak, and the pressure reduced, decreased. Meanwhile, you can see several cracks appear on this ground surface. And in the end, mud was flow out of the soil close to the north side of the wall. So here are more details about this test. This is the mud pressure history, which as shown in the previous slide. Here is the image I cut from that video. On the left, that is a vertical ground movement and a horizontal movement vectors. I used the results from the GeoPIF. So x-axis here is the center line, that is 0 millimeters to 800 millimeters close to the north side of the wall. And the y-axis here is the distance from the entrance of the borehole on the west side of the wall, 400 millimeters to 1400 millimeters. Mud pressure reaches the peak value in a very short time, 102 kPa. At this moment, we didn't see obvious ground movement. The ground movement is very, very small. So on the left, you can see the vertical ground movement. It's less than 0.4 millimeters. And horizontal movement, it's the maximum one, it's about 0.2 millimeters. So imagine you are in the site, you use this horizontal directional drilling. When this mud pressure already reached this critical peak pressure, you probably will not notice anything from the ground surface. So there's no warning for you, even the pressure already reached this maximum value. So here is the earth pressure. These are the results from the earth pressure census. I will show you later, but here that is the theoretical solutions. So because we bury the sensor at the 3 times radius below the inverted borehole, as shown in the previous slide. So x-axis here, that's the change of radial stress, and y-axis is the hoop stress. The black line and the blue line here, that's the theoretical solution and the closed form solution. And the red line here is the results from our numerical modeling. That's pretty close to the theoretical or closed form solution. And here, that is the results from the test. That's the measurement from the earth pressure sensor. It's pretty jumpy, but it's still, you can see the tendency of the data. It's still pretty close to the closed form solution and the numerical model. So after the peak pressure, the mud pressure dropped to, in this image, the drop to 45 kPa. And you can see there's a primary crack appear in the middle of the pit, marked as this white dash line. And the ground movements start to increase to around 6 millimeters, concentrated in that center of the pit, marked as a red color here. And that you can see that the direction of those vectors changed, corresponding to that the appearance of this primary crack. When the mud pressure dropped to around 19 kPa, the moment just before mud flow out of soil, you can see there's several secondary cracks developed from that primary crack, and ground movement reaches the maximum value. So it's about 16 millimeters in the center of the pit, and horizontal movement, it's about 5 to 7 millimeters. In the end, mud flow out of the soil from a shear plane developed close to the north side of the pit, and the ground movement actually dropped from 16 millimeters to 12 millimeters for the vertical ground movement. and the horizontal movement reduced to around 2 or 3 millimeters. After the test, we cautiously excavated the soil like those people did in archaeology. We use a small brush and small shovel to preserve those mud traveling path. So here is the test. Here's the mud traveling path. After my colleague Chiffon and I, we spent a lot of time and effort to preserve this traveling path. So borehole is here in the middle of the pit. Around the borehole, you can see there's a large volume of a primary infiltration zone. We cut a cross section there, and you can see there are 2 small flow tubes, mud traveling one of them, the small flow tube on the right, through a big flow tube to a large area of shear plane. So this shear plane is like sand ridges, so mud traveling in the middle, a few millimeters to the mud X location close to the north side of the pit. So here are some of the results from the tests. X-axis here, that is the buried depth. I normalize this ratio, that H/D, and the y-axis is the peak mud pressure. As this buried depth increases, this peak mud pressure increases as well, which fits our expectation. And then we try to compare this measurement to the existing design equations and numerical modeling. So the design equations, they call this Delft equation because they developed from those researchers from the TU Delft. And they treated this peak mud pressure as the yielding area, which is 2/3 way of the ground surface or halfway to the ground surface. Recently, they used the 5% of a hoop stream at the ground as this criteria, but it has never been confirmed by any physical evidence. Another assumption they made is that the soil stress around this borehole is isotropic, but it's well known that the soil stress on the ground should be an anisotropic rather than isotropic. So you can see there's a big difference between their assumption and our numerical modeling, that the yielding area development in our numerical modeling is much closer to that mud traveling path I just showed in the previous slide. So here are the design equations from the TU Delft, and the results from the modified Delft equation is much lower from this figure. And these blue dots and line here are the results from our numerical modeling, and the black dots and line here our test results. So they are much lower than the results using the Delft equation, a little bit higher when the H/D above around 17, 18. So imagine you want to estimate it is a peak mud pressure, let's say 15, and the design equation will give you is around 150 kPa. However, based on our measurement, it's only around like 70, 80 kPa. So their design equations will give you the results is not that conservative. For the modified Delft equation, when the H/D above 17, the results it's too conservative. So that's why we propose our design equations and try to apply into the field after we verified our numerical modeling. So in conclusions, this is the first known effort to investigate this maximum allowable mud pressures influenced by different factors. And this peak mud pressure increases with increasing of buried depths. We didn't see obvious ground movement when the mud pressure reaches the peak value, and the ground movement reaches the maximum one just before mud breaching out of the ground surface. And the design equations used nowadays is not safe. After we bury the pipe will suffer or experience surface load like from cars, trucks, trains, even airplanes, as well as the geohazard like a landslide, earthquake, new construction nearby like tunnel excavation. But today we'll talk about the pipe experience, the differential ground motion. That's the we try to simulate this problem like those a fort with a deep angle 90 degree. This project, we finished 2 tests. So the first test, we buried the whole continuous pipe in that facility. And the second test, we use 2 pipes connected with a joint because we are interested about the pipe joints in this under this kind of situation. So today I will talk about the first test conducted by my colleague Min, I think probably 4 years ago now, and to see how this pipe behavior under this kind of situation. So this is the facility, we call this a sleep box. So half the box, the ground floor can move downward or upward by the screw jacks, and the other part of the box, the ground floor, is fixed. So we call this a moving side and stationary side respectively. And this box is 1.8 meters wide, 1.8 meters deep, and 7.1 meters long. And there's a window in the middle of the box, so we can use the drill pipe to shoot those images and obtain those soil movements in this close to this fault line. The pipe we use, it's a high density polyethylene pipe with the line corrugated. So this diameter is 0.6 meters with the length 6.4 meters. We install the friction treatment to reduce the friction between the sand and the wall. And sand was compacted into a dense, medium dense state. We also install some targets at the 4 cross sections and the number 1, 2, 3, 4 there inside of a pipe, so we can measure the pipe deformation and the movement during the test. We also attach a strain potentiometer in the end for our backup data. Here is a picture. We buried this HDPE pipe, and here's a picture taken from inside the pipe. You can see we installed this 4 section of targets. Meanwhile, we also install some optic fibers. There's one at the crown, there's another one at the spring line, and the last one is at the invert. So we can use this data to calculate the bending strengths during the test. So here, the vertical displacement of the pipe versus the pipe length. The length of the pipe is 6.4 meters. And in this test, we move the ground floor downward to 100 millimeters in 10 steps. So each step, we move the floor 10 millimeters. So in each 10 millimeters, we stop and use the system to measure those strain from the optical fibers. So here are 3 examples. So it's a 10, 30, 50 millimeters of the bending strengths calculated using the data of the optical fiber sensors. As we can see here, there are 2 peaks. So the tensile peak strength is close to the fault line on the moving side, and there's another peak. It's a compressive strength also across the fault line at the stationary side. And they are not symmetric. The compressive peak strength, the absolute value is actually higher a little bit than the peak tensile strength. That is because the soil capacity of these 2 sides it's different. After we obtain this bending strength, we compare to the design tools that is a standard from American, that are called American Lifelines Aliens ALA standard. They use the design equation called the 3-beam model. And you can see the results. So the y-axis here, that's the peak bending strength, and x-axis here, that's the fault offset or ground movement from 0 to 50. And you can see that the design equations, their data is much higher. So it's too conservative. So why is like that? Because the standard mainly is used for those rigid pipe, for the steel pipes. And another assumption they use in design model is they simulate the soil as a springs, which I'm not a fan about that, but some people use that because it's easy to operate it. And another things this standard cannot capture is those local bending along the pipe, because the pipe we buried, they have corrugated sections. So this design tools cannot capture those data. In the Cambridge, the topic I will study, instead of in the land, this pipe was buried in the seabed, because the engineer was curious about this pipe movement, this breakout force in the different directions, because there's a pipe buried in the seabed to transport oil and gas, the electricity from a wind farm. The depths they bury is not that deep, so they will suffer from those currents. So we try to figure out what is this breakout force for this pipe. And the facility we use is a small scale facility, 1 meter by 1 meter and 0.1 meters deep. And in front, there's the window, so we can take the pictures like we did in the previous topic. So we can move the pipe in different directions, and we can measure the forces during this pipe movement. And then we also install those earth pressure sensors to measure the soil stress around the pipe, and to compare to our numerical modeling, and to see how the design equations performance compares to our test data. So if they're not, we will propose our design equations. So the last topic is pipe rehabilitation. And in North America, you probably will see a lot of these corrugated steel pipes buried under the freeway or the highway. After years, you will see pretty bad corrosion at those invert or hunch locations. So the management or the cities or the government want to rehabilitate this pipe as soon as possible before they just lost their functions. There are different methods to rehabilitate this pipe. The first one is called curing paste pipe. Basically, you just got a liner in this hose pipe, and then you cure, use the hot steam or hot water, and then the liner will cure. And the second method they use a lot is called spray lining. Basically, you just spray the material inside of this pipe, and then you can get a new liner in. And the method I talked today is called sliplining. Pretty straightforward. You just slip the new liner into the hose pipe. That's one project we did in 4 or 5 years ago by my colleague Jake. He wants to test this liner and hose pipe behavior under the surface load. So that's the construction we did in our laboratory with the large scale pit. So here you can see that's the hose pipe. They already bury on the ground. And that's my colleague Caleb. He just helped the technician move the pipe into the hose pipe or slip the liner into the hose pipe. After that, you will see a newness space between the liner and the hose pipe. So we need to use the grouting material to fill this newness space. So that's we install this job pipe from the ground surface to the newness space, like the people did in the field. And we fill the newness space with this concrete. And here, this is the end of the filling. So we can see this blue bags here. We just seal the one end. And we also install a lot of sensors to measure the liner and the hose pipe behavior. Here is the simulation of the traffic load. So you can see there's an actuator and push the loading pad just in the center of this the pipe. And this area of loading pad is the same as the wheel contact area between the wheel and the pavement. So it's the whole process of this slip lining. But today we'll talk about this grouting. So engineer was curious about when we grout that newness space. So what is the critical pressure that triggers the pipe failure during this grouting process? So what's the pipe response when this pressure increases? There are two phrases. So the first phrase one, my colleague Josh Chates, he finished his master in January 2020, and he finished the two tests. And the phrase two, there are another two tests. I almost finished one before I left from Queen's University, before I came here. And I will still analyze the data and to see how this measurements compare to the design equations. And here, that's the facility, different from the pit we use. We use a hoop cell. That's the hoop cell behind this wide pipe. And this in front, this wide pipe is a PVC pipe. The outer diameter is 48 inches, about 1.2 meters. The thickness is from 32 millimeters to 35 millimeters. And the length of the pipe is 1.3 meters. We also install some targets, these black dots around this pipe inside, to monitor the ground, monitor the pipe deformation during our tests, as well as the fiber and the string parts to measure the strains and the deformation of the pipe. So the basic idea is we slip this PVC pipe into that hoop cell behind it and inflated that yellow bladder with water, so that there's a water pressure around this pipe to simulate those grouting pressures. Josh, he did two tests. So the first one is a vertical test. So he can place the pipe in the center of the pit. So we have the maximum newness space. And the second test he did is to put the pipe horizontally. At the beginning, of course, the pipe would touch the invert of the pipe due to gravity. So when the water pumping into this cell, and the pipe will move up to touch the crown of this hose pipe or this cell because of the buoyancy. So we have another situation to simulate the conditions in the field. So here is the test results from the vertical tests. So y-axis here, that is the simulating ground pressure we added around this pipe. On the left, that is the displacement from the invert to crown, the negative, which means the distance between the crown and invert is reduced. On the right part, that's the distance change between the spring line to spring line. The positive sign there, which means the distance is increased during the test. So let me give you more details about this test. And in the middle, on the top in this figure, is the picture we taken during our test. On the right, that is the numerical modeling I did for this test. So on the left is the pressure versus deformation. That the black dashed line there is our numerical results. So at the beginning, that is the red dot there. Nothing happens. Pipe still in good shape, and there's no deformation. After we pump the water into the bladder, we can see we reach the first changing point, and we can see there's a bit of deformation from spring line to spring line and crown to the invert. And when we reach this first changing point, we call this hydrostatic buckling begins. So you can see there's a little bit shape changes of this pipe. And if we continue pumping water into this cell, the pressure actually maintain almost the same as the first changing point when the hydrostatic buckling begins. And however, you can see there's a big deformation of the pipe from crown to invert. So they reduce around 200 millimeters, and the distance between spring line to spring lines they increase around 150 millimeters. After we reach the second changing point, the pressure starts to build up, but with a few deformation. That is because the spring line or the area close to spring line begins to touch the hose pipe. So they don't have a lot of space to move like they did in the hydrostatic buckling stage. When we reach the peak critical pressure, so you can see there's a local buckling happen close to the invert. And here is the moment just before we break the pipe. You can see this local buckling, it's much more obvious. And it's if you see this test in the laboratory, it's very impressive. And you can imagine to break this 3 centimeter or 30 millimeters thickness of pipe into pieces. So here is a comparison between the vertical test and horizontal test. There are some difference, and also they share the same behavior. The obvious difference is these hydrostatic buckling stages. So this plateau in the horizontal test, it's much shorter than this range of in the vertical test. So why is like that? That is because in the horizontal test, just as I mentioned in the previous slide, after we begin our test, the pipe starts to touch the hose pipe. So this space between the liner and hose pipe, it's much smaller than the space in this vertical test. So when we finish the hydrostatic buckling stage, and the liner in the horizontal test didn't have much space to move out, like the vertical test, the pipe in this hydrostatic buckling stage. So here is a table showing our test data versus the theoretical data or existing design equations. So this hydrostatic buckling in our test is the average value. It's almost the same. That is 135 kPa. And from our theoretical data or design equations, so the average one, it's 130 as well. So they are pretty close. So here there's a 2 column. One is minimum thickness, another one is maximum thickness, because the pipe is not that uniform. And the third row here, that is the peak critical pressure. Average one of these 2 tests is around 190 kPa. However, according to the design equations from the literature, this result is much higher, so it's not that conservative. So we have a space for improvement. Another interesting conclusions from this test and numerical modeling is that this and peak pressure, the critical pressure, it's almost the same. Even you change this liner position, you can move around in this pipe, but this pressure is almost the same. But the assumption is that the diameter of the liner and hose pipe are the same. So thanks for my supervisor at Queen's University, Professor Yenmore, and give me lots of this opportunity involving different kinds of interesting projects. And also my supervisor here at Cambridge, Dr. Sam Stanier, for giving me this opportunity to study this pipe barrier in the seabed. Also appreciated the suggestion and advice from Professor Andy Take, Neil Hart, and Mark Tanisnik for them to lending those toys for me to play around in our laboratory. Also thanks for my colleagues, Shifong, Ming, Jake, and Josh for helping me or completing their this research projects, so that I can show all this data today. And also appreciate the technician Graham, Brian, Josh, and Richard for helping me to set up all these tests, and also the other people who helped me during the test. The last one, I also want to thank those unsuccessful and tests and data. Without them, I could not achieve this my PhD and the research results today. And thanks.